Earlier, the subject of rounding errors came up. So we decided to pick a small number that had only a fractional part. Someone said, oh, 1/17th. Great, I'll go with that. So then we want to think about what is the binary representation of that? Well, we start with binary base 2, and we say that we know that we have a 2 to the 0's place, 2 to the 1's, 2 to the 2's, 2 to the 3's, just like in any base. And 2 to the 0 is always a 1's place, 2 to the 1st is itself a 2's place, 2 squared is a 4's place. We're doing a mental decimal conversion here. But those are all whole place values. We don't have any of those, but there's no reason why we can't keep going less significant and say that be on the other side of the radix point, which separates the whole part from the fractional part. In base 10, it's a decimal point, but generically it's a radix point. We have 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. So 2 to the negative 1 is 1 over 2. That's a 1/2's place. 2 to the negative 2 is 1 over 2 squared, 1 over 4, 4th place. 2 cubed, 2 to the negative 3 is 1 over 2 cubed, 1 over 8. There's our 8th place, and so on. Okay, great. Now we ask ourselves, what's the biggest place value we have that goes into 1/17th? In other words, are there any 1/2's in 1/17th? No. 1/4? No. 1/8? No. 1/16th? We're getting close, but 1/16th is still a little bit bigger than 1/17th. So 1/32? Yes, we do have one of those in there. So we're going to keep track of the fact that we have one of those and then take it out, subtract it away. So 1/17th minus 1/32, we need to find a common denominator. We'll multiply the two denominators, 17 times 32. It may not be the smallest common denominator, but it will work always. And so then if our common denominator is 17 minus 32, 1/17th becomes 32 544ths. And 1/32 then becomes 17 544ths. We subtract those and find that the remainder is 15 544ths. Great. Now we keep going and we ask ourselves, okay, are there any 1/64ths in 15 544ths? And so we come over here and we say, okay, there's a question. Find a common denominator again. Multiply 544 by 64, and we find the denominator is 34,816ths. So 15 544ths becomes 960, 34,816ths, and 1/64th becomes 544, 34,816. 960 is bigger than 544, so yes, there is a 1/64th in there. We subtract it away and get the remainder to see if it's not 0. As long as it's not 0, we need to keep going until we give up. If we give up, there's a rounding error. So what we find is that many common, small or large decimal numbers don't have a very precise, small number of bits to precisely represent the number. So the question becomes, can you write a Python script to do that tedious work for us? Okay? And as much fun as it would be to think about manipulating numerals symbolically, I'll give us a break here and say that Python supports arbitrary precision, and in the numerical and mathematical modules section of the standard library is a decimal module and a fractions module. And so if we look at the fractions module, we see that there are a few different ways that we can instantiate an object of this class, of this fraction class. We can do it with a numerator and a denominator, two values there that we can pass into it, pass into the initializer. We can also create a fraction from a number, and we can create a fraction from a string. Great. Okay. I have fired up my Python interpreter over here, and so the first thing I'm going to do is say from fractions, import that class fraction. So import from the module fractions, the class named fraction. Now I can say number, a name I made up, is assigned a fraction object initialized with the string 1/17th. It's an interesting question. What if I didn't put those quotes in there? What if I didn't pass it a string? What if I passed it the expression 1 divided by 17? Oh, I'll save that for you. An exercise for the student. Okay, and then I say, hey, Python, number. Python says, I know what that is. That is a fraction object with a numerator of 1 and a denominator of 17. Great. So now I'm going to say place is defined as a fraction object with the value initialized to 1/32. Then I can say number minus place. And Python says, hey, I know what number is, I know what place is, and I know how to subtract them. There's another interesting thing. How does it subtract a fraction object from a fraction object? Okay. The result is that it is a fraction object with a numerator of 15 and a denominator of 544, which is exactly what we got over here. Okay, we're off to a good start. We also could have said that what would this be like in decimal? So we picked another number, this time a little bit larger, still only fractional, of 0.8. And we said our place values, we can think of them in decimal as 1/2 is 0.5, 1 divided by 4, 1/4 is 0.25, 1 divided by 8, 1/8 is 0.125, and so on. So we ask ourselves, are there any 0.5s in 0.8? And the answer is yes, there is. So we keep track of that here with a 1 in that place. But that means we need to subtract the 0.5 from 0.8 and get a remainder of 0.3. Okay, so we've got a remainder of 3/10 in decimal. And we're asking ourselves, are there any 0.25s in 0.3? And the answer is yes, there is. So we keep track of that. And then we subtract that 0.25 from 0.3 and then with 0.05. 0, we got that precision. And then the question is, are there any 0.125s and 0.05? No. Okay, so there's none of those. Are there any 0.0625s in 0.05? No. Okay, keep track of that. Are there any 0.03125s in 0.05? Yes, there is. So we keep track of the fact that there is one there. We subtract it away and get the remainder. And we continue on asking ourselves, okay, if there is one of the next place value in there, if there is, subtract it, get the difference, and keep going. If there isn't, then there's none of them. We record a 0 here and keep going again until we reach a remainder of 0, in which case we have, as precisely as possible, represented that number. If we stop before we reach 0, there's a remainder, there's going to be a rounding error in that conversion. Okay, so if I come back over here, someplace I have imported from the decimal module a class named decimal. And then I can say number is redefined here, is assigned a decimal object initialized to 1 divided by a decimal object initialized to 17. Okay, and I want to check and say, hey, Python number. Python says, I know what that is. That is a decimal object with this value. Okay, so I can now say that place, my place value is decimal initialized to 1 divided by a decimal initialized to 32. Again, Python somehow knows how to divide decimal objects. It's not dividing those numbers, as we'll see in a moment. But anyhow, if I say number minus place, it says, oh, that's a decimal object with this value. There's our remainder. Okay? So then you're probably wondering, like, why didn't I just say difference is assigned 1 divided by 17 minus 1 divided by 32? Okay, I did that here. And then I say, hey, difference, and Python says, here's the value of difference. What we notice is that that is only a portion of what the decimal object's value was. So the decimal value, the decimal object can represent the number with more precision. In fact, if I look at difference and the type of it, we see that that is an object of the class float. That is using the more typical IEEE 754 algorithms to represent floating point numbers, but with a much less precision. Only probably about 15, 16 digits of precision. And notice I say 15 or 16 because it's not even definite. It depends upon when again you stop looking for differences. Okay, there you go. There you have it. So go ahead, teach Python how to do what we know how to do.